In this video, we're going to talk about ionic equations. So these are chemical reactions, but there's very specifically for things that will dissolve in water. And so examples for us today are going to be Pb, NO3, 2, plus NaI, need two of them, and they're going to go to lead iodide, lead 2 iodide, and sodium nitrate. If we wanted to balance this, what we're going to find is that for every 1 lead nitrate and 2 sodium iodide, we'll make 1 lead 2 iodide and 2 sodium nitrate. Now, when we write a normal, just the chemicals, it looks like this. We say, oh yeah, there's this chemical lead nitrate and this chemical sodium iodide. The problem is, if you actually put solid lead nitrate and solid sodium iodide in a container, they would do nothing. You could grind them for a long time, mix them around. The solids don't really do anything. What does happen, though, is if you were to dissolve them, if you were to make it aqueous. This is why a lot of chemistry is done with liquids. Aqueous solution, dissolved in water, so AQ, aqueous, means dissolved in water. Water is very good at dissolving ionic compounds. Not all ions, and we'll talk about which ones are easy to dissolve and which ones aren't. But many ionic compounds dissolve very nicely in water. This is why sea salt, like the ocean, is salty. Sodium chloride dissolves really nicely in it. Ends up lead nitrate dissolves really nicely as well. So when we write PbNO3 2 aqueous, well, this is very different than lead nitrate solid. A solid would have positive ions, negative ions, positives in series, and given their charges a little different, they'd be a slightly different structure. But this is what we think of when we think of a solid. So this is solid. If you are aqueous, what has happened is water has come in and it interacts with the ions. And so oxygen is partially negative. Hydrogens are partially positive. When these interact, there's a little bit of charge attraction. And while the full negatives are more, if you have a lot of waters, they can add up. You can get significant attraction on those ions. The net result is a dissolved ion looks fundamentally different. We've got our waters here attracted, and you'll have a lot of waters. I'll draw them a little simply here. They will surround those ions and drift them away. And a negative ion, well, you'll just have the water facing the other way. Those partially positive hydrogens can interact with a negative ion. The net result is, we use the little dashes to show attractions, that those ions get solvated, wrapped in water. They get pulled apart from each other. They actually aren't associated anymore. Once you have an aqueous compound, they're not really how we think of for ionics anymore. So lead nitrate aqueous is very different than lead nitrate solid. This leads to some different behaviors. So let's take a look at this reaction again. What's really happening? Well, instead of these things reacting, what I really have is lead 2 plus aqueous and 2 NO3 with a negative aqueous, 2 sodium positive aqueous, and 2 I minus aqueous. So our reactants are actually quite different. By being aqueous, they are free, independently floating ions. Our products then, well, the solid is solid. It actually is associated. So it is lead 2 iodide solid. But my other products are still 2 Na plus aqueous and 2 NO3 with a minus aqueous. Taking into account the fact that they are aqueous, we actually get a reaction that looks more like this. And this is called the total ionic reaction, or possibly total ionic expression. There's a couple different ways to describe it. This is all of the ions, how many, in what state, on both sides. Well, if you ever had a math problem that was x plus y equals z plus x, remember, any change you do to one side, if you do it to the other, it's still equal. So if I was to subtract x on both sides, what I end up with is y equals z. If you have a balanced reaction, this is true. Any ion that shows up on both sides didn't do anything. Well, I've got 2 nitrate aqueous and I have 2 nitrate aqueous. I've also got 2 sodium aqueous and I've got 2 sodium aqueous. They're on both sides. I can subtract them away. I can cancel them out. The result is the only things that don't cancel, well, my lead 2 plus aqueous is not lead iodide solid. They are different. And so I have lead 2 plus aqueous plus 2 I minus aqueous goes to lead 2 iodide solid. So we can cancel out our sodiums and we can cancel out our nitrates. All that is left is the ions that are actually reacting. And this has its own term. This is the net ionic equation, or net ionic reaction, however you want to describe it. These show you the ions that are actually doing anything. All the other ions are called spectator ions. They were necessary to balance the charge in the solids, so they had to physically exist, but they didn't do anything. They just sat around, floated around in solution, and they continue to do that afterwards. So as we have dissolved compounds, we'll have to start considering which ions are actually playing a role and which ions are just along for the ride, which are spectators.